pleasure to welcome Ben Anius, who is giving a course of 6 lectures and maybe at least 2 more talks. A colloquium on Thursday, which will be announced today, I'll announce it today here, which will be on diagrammatics, and a colloquium next week at CMI, probably on Wednesday, on very likely geometric Satake, quantum geometric Satake. That will be the likely title for the CMI colloquium. And,
for dummies, quantum geometric Satake for dummies.
For dummies, yes, thanks. Okay, and I'll give a break with maybe tradition and just give a brief, as I've understood it, his academic background. So he grew up in Boston, got an undergraduate degree at Princeton, then got a PhD with Kavanagh at Columbia, and is now postdoc at MIT. Okay, and is on the job market for a 10-year time.
That's right, so you know it.
Along with Jordi Williamson, he's been making waves, and among their achievements is a proof of the positivity of Castagnoli coefficients for arbitrary constant groups, which
is what we'll do.
Which is what the talks are going to be about.
Exactly.
Yeah.
All right. Well, thanks for the introduction. So in this talk, I want to give a rough introduction to the Castagnoli conjectures, but I'm going to do it giving with as little requirement that you know any representation theory as possible. So if you're not familiar with category O, I'll tell you everything you need to know, at least to treat it as a toy problem. And then the overall goal of the whole master class is going to be to prove these Castagnoli conjectures. Actually, it's going to be to understand and prove something called the Zergel conjecture, which implies the Castagnoli conjectures. So how bad is my handwriting? Is it big enough? Okay. And by the way, please yell, ask questions. You know, this is for you, so don't be shy. So I'm going to start off by giving the background, and then in the second half, I'll really get started with some introduction to the Hecke algebra. So we're going to start the discussion of projectives in category O. So suppose that you have G, some complex, semi-simple Lie algebra. And to such an object, you can usually extract its Weil group, which is a nice finite group. And you can also associate to it a certain category of its representations called O or O sub 0. For those of you who know anything about it, this is the Bernstein-Gelfand category with trivial central character. But if you don't know what that means, then it doesn't matter. Because here are the facts about this category. So first of all, for each element of the Weil group, one has a collection of sort of distinguished objects. One has this thing called the Verma module, or sometimes it's called a standard module. And this thing surjects onto a simple module associated to this particular element of the Weil group. And it in turn is surjected onto by a projective module. So the projective cover of the simple. So you have this for each element of W. And in fact, the Grothendieck group, this thing which encodes how big the objects are in an abelian category of O0, which I'll denote like so, is isomorphic to the, it doesn't have an algebra structure, so it's isomorphic to the group algebra of W, except right now just as a Z module. Do people know what the Grothendieck group is? Good. So, and it has 3 distinguished bases. And if you don't, yell, please. three distinguished bases: the class of simples, the class of the Vermas, and the class of the projectives. So the big question then is, what are the change of basis matrices? So if you have a Verma module, it has a filtration by simples. It has this guy appearing as a quotient, but then various other different simples appearing as subquotients. What are the multiplicities? That's the question we have to ask. And because there's something called BGG reciprocity, if you know how to write this guy in terms of these, then you also know how to write this guy in terms of these. So in fact, you just need to figure out one change of basis matrix.
So what's the highest weight of LW?
The highest weight of LW is going to be W dot 0. So this is the shifted action, W of rho minus rho. Okay. So before we go further into this, I just want to write down some graphical notation to encode these things. So I'm going to encode ZW by putting integers on something called the Coxeter complex. This is just going to be a visualization tool, but the Coxeter complex is going to play a role later on, so I might as well introduce it now. So the Coxeter complex. Actually, what I'm working with is the dual completed Coxeter complex, but that is for a later date. So the example is when G is SL3, then W is the symmetric group on 3 letters. And it has this nice Coxeter presentation where it's generated by 2 simple reflections. So this is the thing which switches 1 and 2, and this is the thing which switches 2 and 3. Modulo certain relations. So this kind of presentation is going to play a major role. And this group acts by reflections on a 2-dimensional vector space. So S is going to be a reflection along this line. T is going to be a reflection on that line. This is a 60-degree angle. And it splits the plane into 6 chambers. And I'm going to label the biggest, the most upright chamber with the number 1. And then you label the other chambers by the element of the group you need to get there. And what I also like to do is, instead of working with this vector space, I like to work with a unit circle in this vector space. So I actually like to work with this sort of hexagon right here, where this is labeled 1, S, T, ST, TS, and STS. So this hexagon here is this Coxeter complex in this case. And so if I take this hexagon and I put some numbers on it, then this is just supposed to indicate an element 2 times T minus 5 times ST inside ZW. Okay. Can everyone see when I write this low on the board? There's no problem with the table. All right. So the second fact is that every projective, so PW, has a filtration whose subquotients are all Verma modules. So it has something called a delta filtration. And in this, and in fact, since it has a filtration, that tells you by counting the multiplicities how big it is in the Grothendieck group. And delta Y appears if and only if Y is less than or equal to W in the Bruhat order, which is a nice partial order on W. And moreover, delta W appears exactly once as a quotient. So for example, we don't yet know what PST is or how big it is. Okay? But we do know that in the Grothendieck group, if you're writing it in terms of the basis of Verma modules, then it has a 1 here, down here in the ST spot. It has zeros here and here because those aren't less than it in the Bruhat order. And it has some number bigger than or equal to 1 in these 3 places. Okay, so we know this much. What we're interested in is finding the precise numbers. I mean, I should have mentioned, we know sort of a lot about Verma modules. They're easy. They're as easy as it gets. They're the sort of baby case. So writing things in terms of Verma modules is really figuring out how big they are. Okay. This is all we know about PST so far. There's one projective that we already know, P1. You know, by the same rule, there's got to be a 1 here and zeros everywhere else. And so in particular, we already know what the entire table of this is. So this is going to be the baby one that we know, from which we build all the others. Yes?
So this, what do you mean, so this ZW is the grouping of them?
Yes. But I'm ignoring an algebra structure on it right now. There's no algebra. It's just a vector. It's just not a vector space. It's just a Z module. So the monoidal structure will come later, but you're about to see essentially where the monoidal structure comes from. Okay? So the third thing is sort of going to be the thing that allows us to come up with something approximating an algorithm for constructing these tables of a projective. So O has endofunctors theta s for each simple reflection. So O group has simple reflections, in this case S and T, for instance. And how do they act?
Can we also do the example for even the simple case G equal to S and 2G?
Oh, I'm just about to do it. So all the examples are just about to come. So these theta s's are called wall crossing functors. This is sort of bad terminology. I prefer wall bouncing, but if you don't know what they actually are, it sort of doesn't matter. Call them whatever you want. Theta s is fine. The point is that they preserve projectives. So how they behave on simples is sort of very complicated, but you know that they preserve projectives. And then finally, they act on the Grothendieck group by right multiplication by 1 plus s. Okay. So right multiplication. How do we understand right multiplication? I'm now going to take this hexagon and draw it a little differently. Okay? So we can see that left multiplication by s is flipping across this line, right? From 1 to s, from t to st. Left multiplication is acting by this reflection. But right multiplication is different. Right multiplication is crossing a wall. And that's why these things are wall crossing functors. So right multiplication by t gets you to here. Right multiplication by s gets you to there. Right multiplication by t gets you to there. STS is equal to TST. Okay? So what I like to do is label the wall by the thing you have to right multiply by, and put an arrow indicating that you're increasing in the Bruhat order. So this is sort of going up by s, whereas this is going up by t. If I had a different color, I would color this a different color. Instead, I'll use squiggles. So this is right multiplication by t, right multiplication by s, right multiplication by s, right multiplication by t. All right? This is a slightly better way of encoding this hexagon. In which case, this rule, right multiplication by 1 plus s, acts sort of locally on any given edge. Okay, and it sends something like a and 0 to a. And it also sends a 0 to the same thing, a. It doubles things across an S wall. Okay. So now we can do a bunch of examples.
So
Yes, the arrow is always in the direction of the Broad order, which has not yet played a role, but will play a role very soon. So I gave you sort of two cases that look the same because I'm about to, they will be different when we discuss the Hecke algebra. Okay, so let's look at some examples. Okay, so we already know what P1 is. It's a 1 here and zeros everywhere else. This is P1. So what is theta s of P1? Well, here's an S edge, and we're supposed to duplicate things over the S edge so we get 1, 1. And this is projective. So it must be a direct sum of indecomposable projectives. These PS's are these PWs are the indecomposables. How could this possibly split into indecomposables? Well, I mean, it can't have any of the PWs for these W because there's a 0 there, but it could have P1 maybe. But if we crossed off P1, it would be 1, 0, and that violates this rule that the things less than W have to have at least one multiplicity 1. So in fact, this thing cannot have any summands other than PS. This thing actually must be PS. Okay? That's right. So this is certainly projective. Okay? And so it's possible that this is PS, or maybe it's PS plus P1. Okay? But if it were PS plus P1, then the size of PS would just be 1 here, 0 there. And that violates the rule that things less than or equal to W have at least multiplicity 1. And this is an easy example where you can just immediately see that something is indecomposable. So this is not true, which is why I'll erase it. So similarly, now we can apply theta t to this thing. This is also going to be projective. Okay? And now we have to average across the t walls. Well, here's the t wall, and here's the t wall. So this 1 becomes 2 1s here and here. This 1 becomes 2 1s here and here. Oh, sorry. Did I draw things correct? Yes, I did. Okay, good. And so, all right, this is ST. Okay, and so again, by exactly the same arguments, this could split into. This could have other summands, but by inspection, it doesn't. Okay, so this actually has to be PST. But now we're going to do one more example, and something interesting is going to happen. We're going to apply theta s to that. We still get something projective. And, you know, here's an S wall, here's an S wall, and here's an S wall. So this 1 becomes 2 1s, this 1 becomes 2 1s, and these ones add together to become 2 2s. And now it's possible that something could split off. Okay? So this could be, what could it be? It could be just PSTS itself, or it could be PSTS plus PS, or maybe it could be PSTS plus P1. As far as we know, these are all possible at the moment. Okay? And so now we have the question which you guys don't have the tools to answer unless you actually know something about category O, which is which of these things is it? Because which of these things is it determines, after we cross off the lower terms, what's left and how big PSTS is. Okay? So this is a difficult question, and in fact, this is the right answer, but there's no real way for you to know this at the moment. Okay? Because each of these 1s contributed a 1 and a 1. So this guy contributed 1 1, this guy contributed 1 1, it becomes 2 2. And so since this is the right answer, that implies that PSTS is this guy minus that guy, so just 1 1 1 1 1 1. Okay? And so we now have the answer, except that if this weren't the case, if it was this, we'd have a different answer. So we almost have an algorithm to figure out our question, but we don't have an algorithm because we can't answer this question. And I'm going to make this even more juicy by giving you. So I'll state it like so. If you take phi s and apply to PW, okay, this is supposed to be PWS plus some ambiguous lower terms. And if we can figure out those lower terms, then we can inductively figure things out. But until we can, we don't have an algorithm. So fact 4 says that for projectives, P and Q, we even know how big the Hom spaces are. So the Hom space from P to Q is a finite dimensional vector space. And its dimension is actually determined numerically by some pairing on the Grothendieck group. So you take the class of P and the class of Q, and you essentially take their dot product. Okay? So I'll do this in an example. So Hom from PS to this thing that we just calculated here. Okay? This thing is projective, so we can apply this formula. Well, what do? We take the dot product between this hexagon and this hot hexagon. So 0 times 1, 0 times 1, 0 times 1, 0 times 1, 1 times 2, plus 1 times 2, you get 4. So this is a 4-dimensional vector space. Okay? Now we know that I'm telling you the answer, that PS is in fact a summand of this guy, which means that there's a and it's a summand with multiplicity 1. So there's a 1-dimensional subspace inside this Hom space, which is the inclusion map, or a scalar multiple of the inclusion map. And there's a 1-dimensional, this is a symmetric form, right? So this also determines the Hom spaces in the other direction. Okay, reversing these two. And there's a 1-dimensional space inside that corresponding to the projection. So how are we supposed to find this? So somehow there's a special 1-dimensional subspace, which is the inclusion of a summand. But finding this and showing that it's an inclusion of a summand is the trick. There, you can no longer work numerically. We've already used everything that the Grothendieck group will tell us. It told us how big the Hom spaces were, but it hasn't told us precisely how they compose. And so that's going to be the question that actually we need to figure out. If we can find a map from here to here and find a map back whose composition is the identity, then we find a summand. Okay? And until we do that, we don't have a summand. So we've reduced the question to some sort of statement about morphisms, and this is as far as we can go. And now we have no algorithm to determine how these things compose at the moment. Later in this class, we will. So to solve this problem, to figure out, say, all we needed to know is sort of the dimension of the summands. To figure out this problem, Kazdan and Lustig sort of came up with a completely different algorithm using something which isn't geometric or representation theoretic at all, just straight algebra. So this is called the Kazdan-Lustig basis. So we're going to get back to things with hexagons in a sec. So be patient. So a Coxeter group, these are going to be the topic of this master class. This is a generalization of a Wall group. Okay? It's a group with a presentation where it's generated by some simple reflections. These are called simple reflections. And they're reflections, which is to say that they square to the identity, and they satisfy these braid relations. So ST, 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 dot, 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 equals TS, TS, dot, dot, dot. So there's M, ST terms here, and MST terms here. So this is, the previous example was M equals 3. So hopefully you've seen these before. If not, there's a lot of exercises about them. And this M number is allowed to be 2, 3, 4, 5, etc. It can also be infinity. When it's infinity, you just omit this relation. So there's plenty of infinite Coxeter groups. And what you should think is that S is some reflection across some plane, T is some reflection across another one at angle theta, ST is rotation by 2 theta, so that st to some power being the identity, so this equation is equivalent to st to the mst is 1. That tells you that rotation by 2 theta, so m encodes the angle. All right. So, the group algebra has a presentation where it's generated by these simple reflections, and modulo the braid relation, this thing right here is the braid relation. The braid relation's 1 for each pair st. And then the fact that s squared is 1 can be rewritten, now that we have addition and subtraction, as saying that s has eigenvalues plus or minus 1. Okay, so the Hecke algebra is a ZV V inverse deformation so instead of calling the generator S, we'll call it HS. And we still have the braid relations on these HS's. So HS, HT, HS, HT is equal to HT, HS, HT, HS. But instead of having eigenvalues plus and minus 1, we say that it has eigenvalues minus V and plus V inverse. Okay. So there's many, many different conventions for how to renormalize things here. This is the best. In my humble opinion. It's going to be the easiest to describe things coming up. Okay. So the Hecke algebra has a basis, H sub W, which is supposed to be H sub S1, HS2, dot, 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 HSD, when W is S1, S2, SD is a reduced expression. It is a shortest possible way of writing W in terms of the simple reflections. So this is not supposed to depend on which choice you made because of the braid relations. And so we're going to encode elements of the Hecke algebra in our little hexagons, 1 minus V squared, V to the minus 3, and V. This is supposed to be 1 minus V squared times H1, which is the identity, plus V to the minus 3 HS, plus VH, ST. Okay. So there's one important other structure that this thing has. It has a bar involution, also defined by Kasdan-Lusztig. So this is going to be sort of our notion of being projective. It's going to relate to our notion of being projective, or being self-dual is. So this is an involution. So it's in particular an algebra homomorphism, and it's determined by the fact that it sends V to V inverse and HS to HS inverse. So I have explained why HS is invertible, but in fact it is. So exercise is compute HS inverse. And now we're going to finally get back to something algorithmic. Okay? So the next exercise is that there's this particularly nice element, HS underline. Yes. Sorry, where? Oh, yes, HT. Thank you. And this is probably TS, isn't it? That's correct. Oh, was that correct? It is TS? It doesn't matter. Yeah, it's right multiplication by S, right multiplication by T. That should be ST. Okay. So this thing right here is self-dual. That is, if you take its bar, you get itself. And so multiplication by this thing preserves self-duals, just like acting by theta s preserves projectives. Okay? So how does, and the final exercise is that right multiplication. So this is the analogy to 1 plus s. If v is 1, then this is 1 plus s. Right multiplication by hs acts as, so it sends, and here the Bruhat order really matters. Okay? So if s brings us up, a is a polynomial now, a Laurent polynomial in V. And it sends this to, well, it takes a across the wall, and what it leaves behind is a times V. Whereas if s brings us back down in the Bruhat order, then it still takes a across the wall, but it leaves behind a times V inverse. Okay? So this is the new V-deformed rule from before. You said v equals 1, you obviously get what you had before. And now, we're going to say what we're trying to compute. There's this theorem of Kazhdan and Lustig that there exists a unique basis, h underline w, to be distinguished from this thing right here, which is h with no underline w. So this is called the standard basis. And this is called the Kazhdan-Lustig basis. Which satisfies that HW is self-dual, and 2, that HW is HW in the standard basis plus lower terms. So these are all less than W in the Bruhat order. But the important fact is that each of these lower terms, the coefficients that appear, are not just polynomials, but they're polynomials in, not even Laurent polynomials, but true polynomials with no constant term. Okay? So, another way of writing this, in our example from before, h underscore st has to have a 1 here, zeros here because they're bigger than it in the Bruhat order, and then things that are all real polynomials up there. Okay? So the uniqueness is a fairly nice exercise for someone who's never played with Hecke algebras before. But to show the existence, actually, we'll just basically use the same algorithm that we did before when examining projectives, and you'll see a big difference. Oops. So clearly, h underscore 1 is just h1. If you have a 1 here and zeros everywhere else, you're self-dual because you're the identity and you satisfy property 2, so that works fine. So now let's right multiply. This is the identity of our ring. Well, let's right multiply by hs. Oh, you get 1 and v. Lo and behold, that's self-dual, and it has the property we want, 1 there, strictly positive before. That's why this was h underscore s. Now let's right multiply by ht. So this 1 goes up this wall and leaves behind a v. This v goes up this wall and leaves behind a v squared. And lo and behold, this is a 1 here and all positive polynomials there. So this is, in fact, hst. And now we do one more time, and the interesting thing is going to happen. So hs, ht, hs. So the 1 goes up, leaving behind a v. The v goes up, leaving behind a v squared. the v squared goes up, leaving behind a v cubed, but then the v goes down, leaving behind a v times v inverse, or a 1. Okay, so there it is. Now this cannot be. This is clearly not HSTS because there's a constant term. And we're not allowed to have a lower constant term. So to get something, maybe we subtract this constant term, okay? But we can't just subtract the number 1 here, because then we're subtracting h, normal h of s, which is not self-dual, and so the result won't be self-dual. But if we subtract something that's self-dual, like hs, then we'll get something that's self-dual. And what remains is this guy minus this guy, so we cross him off and we cross that off, and we end up with some very nice picture. 1 v squared, v cubed. Okay. So just looking at a table of numbers, it's very hard to tell if something's self-dual. Okay? It's really a pain. But building it up in this way, you're guaranteed to have something that's self-dual. Okay? A miracle happened. A great miracle happened here. Yes, I mean, this is, basically this is just the Bruhat order. It's the length difference is the power of v. But this is not always that easy. So Verma, in his original thesis, conjectured that all the numbers were 1. All the multiplicities were 1. He was wrong. In SL3, all the numbers are 1. In SL4, you start having some interesting things show up. And SL4 is the first time something happens. This is, it's actually a theorem of Patrick Polo that every possible polynomial that you can think of with a no constant term is a Kazdan-Lustig polynomial, is one of these coefficients. Okay, so they are arbitrarily complicated. For type A. Every polynomial in the world is a Kazdan-Lustig polynomial. Well, there has to be some sort of parity, so the it's v squared or v to the 4th or v to the 6th. It depends on the length difference, and the height of it is capped. But eventually, any polynomial will appear, any reasonable polynomial. I'll finish writing this. Okay, so here we had a genuine algorithm. Okay, unlike there's no wishy-washiness here. We knew exactly what we had to subtract, because by splitting this number 2 into 1 plus v squared, we now have exactly this constant term. This number 1 here told us what had to come up. And so I'll point out that this construction actually works because the statement is that if you take hw, whatever it is, and multiply it by hs, when s increases w in the Bruhat order, then this is going to be hws plus a bunch of lower terms. And in fact, these lower terms, they have some sort of coefficients. So these are usually called mu coefficients. Okay? But these things are actually all integers. They're not polynomials. They're integers. Okay? And why? In other words, when I had this, I had a 1 here. And when I write multiply by hs, that 1 is going up. So it's leaving behind a v. Now, the only way that you could get here you have all things with no constant term. And the worst that can happen is you go down, which means you multiply by v inverse. So the worst, you could go from having no constant term to having a constant term, like we did here. But you're never going to go to having v inverses. Okay? So this thing right here has no v inverses. Okay? So all you need to subtract is constants times times lower things to get rid of all the constant terms. Sorry. Yes, this is why, there's actually some more conditions on this why, but we won't go into it. It's not so important now. So these things are nice integers. All right, cool. And so the conjecture of Kazdan and Lustig is that this algorithm is supposed to actually tell you what happened in category O, that if you take these polynomials and evaluate at v equals 1, this is supposed to be the multiplicity of delta y in PW. Cool. And I'll make one other point clear. The Heck algebra of W also has this sort of dot product, this pairing. This pairing has certain properties, but it's easy to evaluate on self-dual things. So this is the same dot product. So the point is that hx, hy is actually delta xy. The standard basis is orthogonal. Okay. So now, if you did this same calculation from before, and you paired h underline s, h underline t, h underline s against h underline s, okay, then instead of getting the number 4, you get 1 plus 2v squared plus v to the 4th. Okay? So somehow the fact that there's this one-dimensional guy showing up is now very clear. So numerically, we know how big, how many things are supposed to split off. We just don't know in category O that they do. Okay.
That one corresponds to the HS.
Yes, exactly. So, you know, HHS is HSTS plus HS, right? And in fact, it's an exercise. I'll say this in a second. So the point of this, actually, this sort of weird splitting of the number 4 into these things, is that Hom spaces in O are secretly graded. I mean, they're not graded, but there's a way to make them graded, such that a composition is graded. Okay, and so this is actually a graded dimension. Okay, one map in degree 0, 2 maps in degree 2, and 1 map in degree 4. Okay, and any inclusion or projection is a degree 0 map. Okay, so obviously you're limited by the constant terms that can appear. That tells you how to find the right one-dimensional space. If you put the grading on it, it's just the degree 0 maps. So this is showing this is actually the easy part of the Kasdan-Lusztig conjecture. The hard part is still saying that, okay, so I have this one-dimensional space of degree 0 maps. If I compose the map in with the map back, do I get the identity or do I get 0? Maybe it's not a sum n. Okay, so you still have a lot of work to be done. Okay. So you know, there's some kind of graded category O, which is really kind of annoying to describe. People usually write O with a Z up here, but we're not going to talk about this. And this graded category O, its Grothendieck group really is the Heck algebra. So that theta S acts by right mult by H underscore S, as you might expect, and that the graded dimension, now the true graded dimension of P and Q is the pairing on the Grothendieck group. So there's a nice exercise here, which is that, okay, so I told you that these things were an orthonormal basis. Okay? I didn't tell you how this was linear. In fact, this is V linear in the second term and V antilinear in the first term. Okay, so you multiply by V here, it comes to a V here. You multiply by V here, it goes to a V inverse. We'll talk about this more in a sec. But you can compute that if you actually pair not the standard basis, but the Kasdan-Lusztig basis, then they're graded orthonormal. Okay? So this pairing, you know, it'll have a constant term if and only if they're the same. And then everything else will be in strictly positive degree. So this is to say that if you had objects in this graded category O satisfying this, then the Hom spaces between them are all in positive degree. And you only have a degree 0 map if you're looking at the endomorphism of an indecomposer. And this will make it really easy to figure out how things split in your category. So if you have objects whose class in the Grothendieck group is the Kasdan-Lusztig basis, then you know a lot about them, is the point. Okay? So the Kasdan-Lusztig conjecture, as stated over there, is equivalent to the statement that the class of PW in this graded category O is H underscore X. Yes. Thank you. All right. So how would you go about proving this? This is where you get this idea of an intersection form. So, suppose we know it that, that the class of PW is HW, or let's say, sorry, the class of PY is HY for all Y less than WS. So particularly we know it for W. Okay? Now, as we've written before, HW times HS is HWS plus these mu coefficients. Okay? And theta S of PW is PWS plus some lower terms. Okay? But you know the class of this in the Grothendieck group. The class of this in the Grothendieck group is this, which means that you know how big the Hom spaces are. Okay? And so this thing right here is actually the dimension of the Hom space in degree 0 from Py to theta S of Pw. And it's also the dimension of the Hom space backwards in degree 0. Okay? So, in fact, these two spaces are actually isomorphic under some sort of adjunction isomorphism. So that means that you actually get a pairing. You get a pairing from Hom Py to theta S Pw across the going back, which is the same space, by composing to the endomorphisms in degree 0 of Py. Okay? And this thing is a positively graded ring that only has the identity map in degree 0 because of this fact. Okay? So that means that endomorphisms in degree 0 is just, C times the identity. Or if we're working R linearly, R times the identity or something. Okay, so we actually get a bilinear form on this vector space. Okay? And so the statement is, what is the rank of this form? So, if the Hom space were one-dimensional and the composition gave you, there were two things that paired to 1, that means you have an inclusion and a projection. And in general, if it's 5-dimensional and the form has rank 3, then you can construct 3 orthogonal inclusions and projections. So it will be a sum and a multiplicity 3. Okay? So this is a vector space whose dimension is exactly the multiplicity we're hoping that it has. Okay? So what we want is for this form to be non-degenerate. So if the pairing is non-degenerate, this thing is called the local intersection form. Local intersection form, which is what it corresponds to in geometry. So if this local intersection form is non-degenerate, can construct I forget, many copies of Py as summands of theta S Pw. And if this is true for all y, then what's left over after we chop off all the rest of the summands has the right size. If true for all y, then the Kazan-Lusztig conjecture is true. So we've reduced the Kazan-Lusztig conjecture to a morphism theoretic statement, which is the non-degeneracy of these intersection forms. Now, we've done sort of everything we can do in the Grothendieck group, and we have to actually compute and somehow prove that these things are non-degenerate. So proving that a form is non-degenerate is very difficult. And it turns out that in the proof that we eventually do, we take this vector space and we embed it inside another form. And we show that that other form, the global intersection form, is positive definite or negative definite. So when you embed a vector space inside another one, and you restrict a form, if a form is non-degenerate, it can restrict degenerately to a subspace. But if a form is positive definite, then it restricts positive definitely to a subspace and therefore non-degenerately. So that's going to be a crucial tool in the argument, and some sort of non-degeneracy. Okay. The final thing I'm just going to say in this sort of half, we're going to take a break and then come back, is that I said that we didn't need to know anything about representation theory. And you don't. Okay? So we don't really need to know anything about O, category O, which is only defined for Wall groups. I was doing this Hecke algebra stuff for an arbitrary Coxeter group. Okay? But this Kazan-Lucy conjecture is only for Wall groups. Okay? So we're not going to work with category O. We're going to instead work with Zergel bimodules. So category O is kind of a pain. And people who like to play with category O, there's a lot of fun things you can do. But computing Halm spaces in category O is very hard. Understanding objects in category O is often easy. But understanding the actual morphisms between objects is very hard. And it's clear that that's what we need to do. Now, Zergel bimodules instead have the advantages. They have a couple advantages, which is that it's obviously graded. Right? We somehow need to find the space of morphisms in degree 0, and we'll restrict our attention to that. Well, it's hard to do in category O, but it's very easy to do for Zergel bimodules. It's easy to define and easy to play with. It requires very little background. And I guess most importantly, it works for all Coxeter groups. So it has a streamlined definition for everything. Zergel originally defined them in an attempt to give a sort of simpler proof of the Kazan-Lucy conjecture. So what we've done is realize his dream. And I guess this is a good place to stop.
And how easy is it to see that Zergel bimodules mirror?
Yes. So in fact, there's a functor, a so-called Zergel functor, from O0 to Zergel bimodules. Usually denoted V. But what this is, it's pretty easy. It's Halm from the lowest projective. Okay. So when you take Halm from an indecomposable projective, this kills every simple except its simple. Okay? So this is a terrible functor. Okay? It kills every LW except for LW0. Okay? And it takes every Verma to a one-dimensional vector space. Okay? But it's fully faithful on projectives. So Zergel's original paper, which is actually not so bad. It's actually quite readable. Well, so part of it is quite readable. His definitions of Zergel bimodules is quite readable in that paper. But the proof that this is fully faithful on projective goes to Harish-Chandra bimodules and is quite technical. However, once you know this, you just have to ask about the image. Okay? And what happens is that acting by this theta S turns into acting by some sort of basic bimodule BS there, and so it becomes easy to describe the image. So that's the reason that you can work with Zergel bimodules. I don't really need it for today, but I will need colored chalk in the future. All right.
Okay, so we get back, and so Rania shows us that some of the initial category O stuff was just a reproduction. So this, now we will start with Hecke algebra and local bimodules from scratch.
Exactly. So that was the broad overview, and now we're going to do some nitty-gritty from the beginning. Also, we've agreed that there will be a prize for the person who is not Raghavan, who asks the most questions.
And I guess not depend on.
Yes, yes. Ask as many questions as you want. Okay, KB, though, you're in the running. All right. So let's just talk about the Heck algebra. Okay. So let's fix some notation that I'm going to use for the whole time. So we're going to start with a Coxeter system. Coxeter system, which is the Coxeter group itself and the choice of simple reflections. Now, if we have a list of simple reflections, S1, S2, dot, 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 SD, an ordered list, this thing is essentially giving us a word. And I'm going to write W underline for this word. And usually I'm going to abuse notation. Just write it as though it were a product. But when we have the underline here, I'm really indicating that the order matters, not just the product in the group. Okay? So if I write it without the underline, this is an element. But with the underline, I actually mean the word itself is important. So an expression is reduced. And so I'm going to use rex for reduced expression, because it's going to show up all the time. If D is minimal, this length is minimal amongst all expressions. Expressions for W. There's a fact, which is that all rexes, all reduced expressions, are related by the braid relations. So remember that there's two relations in this Coxeter group. There's the quadratic relation that S squared is 1, and then there's the braid relation, like SDS equals TST, or STST equals TSTS, etc., depending on what M is. So obviously, arbitrary relations will be related by both of these, but reduced ones, you only need the braid relations. And this is the reason that these HWs were well defined. But remember that HW was defined to be, all right, HW. So choose an expression, a reduced expression, and take the product of these simple of these generators, HS. So when I put an underline here in a subscript, I really mean take the product of the things in this sequence. Okay? And the reason that this does not depend on the rex that you choose is because these things obey the braid relations. They don't obey the quadratic relation, but they obey the braid relations. Well defined, independent of the choice of rex. So a sub-expression.
So by definition, you define it as.
Yes.
By definition,
Yes. I defined this by choosing a reduced expression and then taking the product, and it didn't matter which one you chose. So a sub-expression is just going to be choosing some of these guys. And instead of just writing down which ones we're including, what we're going to write down is a sequence of zeros and ones, where the ones are what we take and the zeros are what we don't take. Okay? So I'm going to write it like this. A sequence E inside W, or maybe a pair WE, where E is a sequence of zeros and ones of the same length. Okay? So given a reduced expression, or sorry, given an arbitrary expression and a choice of W, zeros and ones, we're going to let this product be the product of S1 to the E1, S2 to the E2, etc. Be the thing that this expresses. So this is an element. And the Bruhat order is nicely given by the notion of a subexpression. V is less than or equal to W if and only if there exists a reduced expression for W and some subexpression such that W to the E is V. So that's how the Bruhat order is defined. And we'll now see why it's important. Okay? So in the Hecke algebra, we're going to write H underline W underline, again, to mean a product of H underline S. So this is the product of the Kazhdan-Lustig generators rather than the standard generators. That's what these stupid underlines mean. Okay? So this is, remember, this is V plus HS. So H underscore S1 is V plus HS1 times V plus HS2, etc. Okay? So you can see that when you take a product of things like this, the terms which appear will correspond to subexpressions, right? I mean, you take this guy and you don't take that guy, but you have a V instead, and you take that guy, okay? And then also when you multiply, if S1 was equal to S3, and you did HS1 times V times HS3, HS1 squared is some linear combination of HS and the identity, so that's another way to get subexpressions appearing. But it's clear that the only terms that appear are going to be less than W in the Bruhat order, or if this is a reduced expression. Okay. And now we're going to figure out what. Exactly, that's correct. So now we're going to figure out actually a formula for the coefficients that appear. So this is great practice. There's a bunch of exercises on the exercise sheet that let you play with this. Yes, this is the definition. Yeah. When you have a sequence, yeah. And in general, we're going to use similar notation to whenever you have a subscript with an underline, it means take the product of the things in order associated to the simple reflection. Yeah. So if you don't have the underline, this is supposed to be the Kazhdan-Lustig basis element. Whereas with the underline, it's a product of the Kazhdan-Lustig generators.
You can use a different notation for V or W, the other V, because here there is a V.
Here there is a B.
V less than W.
All right.
There is an input of the last book, there is a V, there is a V.
Yes, exactly. V will never be an element. Hopefully not. So some people use Q, right? But some people have Q, which is V to the minus 2, and so it's best to avoid Qs, I find. Okay, so here's a definition. Given a subexpression, its defect. So this is the Diodar defect. Is given as follows. So you should think of the reason that we encode a subexpression with zeros and ones is that you should think that the things that you don't do are as important as the things that you do. Okay? So you should think of a subexpression as E gives a Bruhat stroll. This is our little term. A stroll is like a walk, except that you don't just care about where you walk. You spend a lot of time looking at the scenery. Okay? So if EI is 1, you go there, and if EI is 0, you look longingly, but don't go. Okay? So and what we're going to do is we're going to label it with an up if it goes up in the Bruhat order. in Bruhat order. And a down if it goes down in Bruhat order, regardless of whether you went there or not. So let's do some examples. So W is going to be the expression STS, and MST is going to be at least 3. Okay, well, let's just take, if you want, we can take MST as 3, so that we're in the case of the symmetric group. Okay, so here is our, we have 1, we have S, T, ST, TS, STS, and the Bruhat order goes up. Okay, so this is S3. So let's take E to be 1, 0, 0. Okay, do it, don't do it, don't do it. So we're starting at the identity. Okay, the first thing we do is we take S and we do it. So we go up to S and we went up. So this is an up one. Okay, the next thing we do is T. T would bring us up. We don't do it, so we stay still, but that's an up. Okay, we're still here. We just look that direction. And then the next thing we do is an S. We don't do it, but that would have taken us down. Okay? Whereas if E was 0, 0, 1, this is another expression. So this is an expression for S. All right? WE is just S. That's where we ended up. Okay? Here's another expression for S. Okay? But in this case, we start at the identity. We look up. We don't go. And now we're still at the identity. We look up. We don't go. And then we look up and we go. That's up, up, up. Okay? So the defect is +1 for each up 0 and -1 for each down 0. So the defect encodes where you wished you went, but you didn't go. Okay? So here, this thing has defect +1, -1. So the defect is 0. Whereas this thing has defect +1, +1. So the defect is 2. Okay? And these are the only expressions for S. The only sub-expressions for S. So this is something you can really play with, I hope. I hope you're convinced this isn't so hard. So the Diodar formula, then, says the following thing, that this product, when you break it all out, is equal to the sum over sub-expressions of the end of the sub-expression, where you end up, and the coefficient is v to the defect. Maybe this is the defect of a sub-expression. Okay. So we can compute now what is HS, HT, HS. So this is something we computed before using the hexagon method. This was 1 v squared, v squared plus 1, and v cubed plus v. Okay? And if we want to know this coefficient here, we're at the S spot. So we find all the sub-expressions for S, and we compute their defects. Well, we just did that. The defect was 0 and 2. And so we should get v to the 0 plus v to the 2. And so exercise is to compute the rest. So as you said, there's a unique way to get W. If this is a reduced expression, which it is, there's a unique way to get STS, and that's 1, 1, 1. And ones never contribute to the defect. Okay, so you're going to have defect 0, and you're going to get the number 1 there. Okay. And as you can see, there's a unique sub-expression for ST, and a unique sub-expression for TS, and a unique sub-expression for T, but there's multiple expressions for S and for the identity. Okay, great. Well, this formula is really wonderful, and soon enough, I guess next week, we'll categorify this. Whatever that means. Okay, so great. So now there are a couple more important structures on the Hecke algebra. But this is going to be the main tool that you use to do computations. So the Hecke algebra has 3 more structures, which we sort of already alluded to. And they're all sort of related to each other. So there's omega, which is an anti-involution. Are there any questions, by the way?
So this is a multiplicity of the some point in the supergravity formula.
Yes, yeah, exactly. That's exactly right. This as well. So this thing right here is a Bott-Samuelson variety, actually. So it's what you're computing is the dimension of a fiber over an orbit in a Bott-Samuelson resolution. Mm-hmm.
On the right hand side.
Yes, this thing right here is an element, right?
Yeah,
So
that's not an experiment.
exactly. Yeah, this is the one drawback of this notation. So we can't. This is the best notation we could come up with. We tried. It's So I mean, the problem is the H and the H underscore. I already hate that, but it's Jordy insists on it, so I try to follow it, and it's in the papers. I usually use like little lowercase b to indicate the Kazan-Lusztig basis, but H underscore is what's in the literature, so it's best to get used to it.
Here you are using one radius expression and then use that.
Exactly. Exactly. Okay. So the Hecke algebra has 3 more structures which are all related to each other. So the first is this anti-involution. So an anti-involution is something for which W of AB is W of B times W of A. And this is defined to be the anti-involution such that V goes to V inverse and H underscore S goes to H underscore S. Okay? And so it's an exercise, and it's a good one to compute from this, what happens to HS. Okay? And the actual answer is that HS goes to HS inverse. Okay? Which means that what happens to HW, right? So HS, HT is then going to go to, since it reverses the order, HT inverse, HS inverse. Okay? But this is HST, and this is just HST inverse. Okay? So HW actually goes to HW inverse. So on the standard basis, it's easy. And on the Kazan-Lusztig basis, it's also easy. Okay? But on other things, it's weird. Then you have this epsilon, which is going to be the standard trace. Okay? And this is going to be a map from the Hecke algebra to polynomials. I'm going to I'm just going to write V plus or minus to save some time, as opposed to V comma V inverse. Okay? This is the thing which takes the standard basis, which reads off the coefficient of the identity in the standard basis. Okay? So for instance, epsilon of HS, HT, HS is coefficient of the identity, which is V plus V cubed. Okay? And again, if you have a composition of Kazan-Lusztig generators, you can use the Diodar defect formula to compute the trace. That is, you find the sub-expressions for the identity and you take the sum of their defects. Okay? Now there's a claim, so I'm calling it a trace. And a trace has to satisfy that that epsilon of BA is the same thing as epsilon of AD. Okay? So this is not immediately obvious at all. And the way that you prove this, and it's also in the exercise sheet, is what you want to compute is epsilon of hx times hy, or maybe hx times hy inverse. I forget which makes it easier. Okay, so the point is when you take hs and multiply it by hs, okay, remember this quadratic relation. I'll remind you, hs plus v hs minus v inverse equals 0. And another way of saying that is that hs squared is v inverse minus v times hs plus, or minus, yes, plus 1. Okay? So as you're multiplying on your way up to get hx, okay? So to get h, suppose that we do hst times hst. Okay? So hst is hs times ht. hst is also hs times ht. Okay? We're trying to get a coefficient of the identity. So this is going to just bring us straight up. Right? I mean, hs times 1 is hs, and now we're at hst. And then we multiply by hs. And that actually, let me do ts. Sorry. Okay? Then we multiply by ht, and when we put these together, there's two terms. One in which we replace the two ht's with a single ht, and one in which we get rid of both of them at the same time. If we replace it with a single ht, then this hs is never going to bring us back to the identity. So the trace is going to be 0. Okay? Whereas if we replace this with nothing, then we're down to hs times hs. And again, we have to replace that with nothing in order to get a coefficient of h1. Okay? So in order to get, here we went up, 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 up. We're at hst. To get back to the identity, you have to go down, 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 down. Okay? So you can use this to figure out how these compute. If y is not the same as x inverse, you're going to get 0. And if y is x inverse, you're going to get 1. Okay? This should be delta x y inverse. Okay? And because of that formula, which is obviously symmetric, this is going to be symmetric. Okay, so actually working that out for sure is an exercise. And the third thing is this pairing, which I mentioned. This is called the standard pairing. So you can define it in multiple ways. But I like to define it like this. It's actually epsilon of w of a times b. Okay, and this puts them all together. Okay? But the point and the claim, which sort of follows from this argument that I just made quickly, is that hx hy is delta xy. That's putting together this observation with that observation. And then the exercise, as I said, this is an easy exercise, is to show that the Kazdan-Lustig basis is positively graded, delta xy plus vzv. Right? As I said, this is sort of a dot product between two hexagons in this example. And when you take a dot product, you've got a single term which is 1, which can pair against another thing to be 1. And then every other term is of positive degree in the Kazdan-Lustig basis element. So when you pair things of positive degree, you get something of positive degree. And the sort of one important feature that remains about this pairing well, I can say fact, but it's sort of built into the definition. And the reason this is important is that HS, this Kazdan-Lustig generator, is self-biadjoint. Okay? Which, This is for each symbol or function. Okay? So the statement of self-bijunction is that if you multiply by hs on the right, here, it's the same as multiplying by hs on the right here. And if you multiply by hs on the left, that's the same as multiplying by hs on the left. And again, it's quite easy to see from this formula, all that you do to get from one side to the other is you apply omega. And omega fixes hs. Okay? So this fact, when we translate it into Hom spaces, is actually mirrored by an isomorphism. That the Hom space from the thing categorifying this to that, which essentially says that this hs corresponds to this functor theta s, and it's saying that theta s is adjoint to itself as a functor. Okay, so once we get there, that's going to be the meaning of this. This is not a meaningless statement. Okay, but again, if you want to actually compute these things, it's not so hard to do. And when you're trying to figure out the size of Hom spaces, you're going to need to be able to compute this, right? So if you want to compute, hs with hs, well, to compute this, you bring this over to that side. Because by adjunction, this is the same thing as hs with 1. Or I could have actually brought them all over to this side if I wanted to. Okay? And that's, whenever you're pairing something with 1, maybe if a is 1, you're really just taking epsilon of it. Okay? So this is actually just epsilon of hs, which again you can compute with the Diodar formula. Okay? We can do that right now. It's pretty easy. To get the identity, you need to either choose nothing or choose any two of them. Okay? Now, each of these is an up. Because you're at the identity, and then you're at the identity, and then you're at the identity. So this is defect 3. Here, you go up to s and back down to the identity, and so this would go up again. Here, you're at the identity, so this 0 is an up. But here, the 0 is when you're at s. So this 0 is a down. Okay? And therefore, this is supposed to be v inverse plus 2 times v plus v cubed. Okay, so this is very similar to the polynomial I write down as this Hom space earlier. you can go home and compute that hs, ht, hs with hs, when MST is 3, or actually even when MST is bigger than 3, is supposed to be 1 plus 2v squared plus v to the 4th. Okay, so you can do these computations now. Not so hard. Mm-hmm. Yes, when v is 1, they are. Yeah, this is g goes to g inverse. This is take the usual co-unit. Yeah, and this is the just orthonormal.
Just wondering if there are other specializations which also are nice to look at.
Are there other specializations of v that really matter?
Maybe proof of unity or something. I don't know.
Right. Right. I don't know if there's anything particularly exciting that happens out of root of unity. That's a very good question. We can categorify the Heck algebra to root of unity, too. That's a totally different story, actually. It's really interesting. But a story for another day. Good. So then, let me just quickly look at my notes to make sure I'm not forgetting. They're over here. What happened? Oh, doesn't matter. So if these HS's generate, then so do the Kazdan-Lustig generators. I've been calling them the generators. And the question is, what are the relations? Okay. So this is actually a more interesting and harder question. So the quadratic relation is easy. Okay, so a nice exercise is to go home and compute that HS is actually V plus V inverse times HS. Okay, that is nice and straightforward. So this quadratic relation becomes this quadratic relation. But we need some sort of relation to replace the braid relation. And this is going to be much more difficult. So I'll give it to you for m equals 4. For m equals 4, it's actually HS, HT, HS, HT minus 2 HS, HT is equal to the same thing with T and S switched. Two. All right. That's weird. Why? But it's not so hard once you know what you're looking for. So I've put this. Am I doing something in my pocket? No. Try to keep my hands out of there. All right. So here's the dihedral group with m equals 4. Okay? And we can do this whole argument. You know, now we're doing it on an octagon instead of a hexagon. Okay? There's the Coxeter graph, and we can do this whole argument as before. Okay? But the claim is that actually the Kazdan-Lustig polynomials are really easy. So HW is actually just the sum over all y less than or equal to w of hy, the standard basis, with the coefficient of v to the length of w minus length of y. So in other words, if we were interested in h of STS, and when we put a 1 there, everything down here is less than it in the Bruhat order, because TS is a sub-expression, ST is a sub-expression. And all we put is the difference in length. So V squared, V cubed. So again, using the same algorithms that we built up, this is easy to show. The other thing that's easy to show is that if, let's do, you know, ... TST or something. Okay, so if we have some alternating expression that ends in T, and then we add an S so that we go up, okay, then you're supposed to get this guy plus lower terms. Okay, but you only get one lower term. Okay, let me do an example. If we take this guy and multiply by HT, okay, then it's supposed to give you two terms. One where you add the t to the end, and one where you subtract the s from the end. Okay? And if we actually do this example, which would be easier in colored chalk so that I could have both the original and the fun, you'll see that this one goes up and you get a 1 here. And this v goes down, so you get a 1 there. Those are the only ones that you end up with. Okay, this v goes up, so you lose behind a v squared. So the only time you're going to get a 1 is here and there. So you're going to get HSTST plus HST. So when you take any Kazdan-Lustig basis element and raise it, you get the higher term, but your lower term is just crossing off the last index. Okay, so add an s to the end or subtract a t from the end. There's sort of two things you can do to end up with s as the end of your expression. Okay. So this then says, okay, how do we find an expression for the longest element? Okay, so to find an expression for the longest element, W0 is usually the way of writing the longest element, you sort of start at the identity and build up piece by piece. And so you can see in the m equals 4 example, you'll get that this is actually hs, ht, hs, ht, and as you did this process, you ended up not just getting, this thing is equal to him, but you also got some lower terms. And the lower terms that you got are twice hs, ht. Okay? And so that would be building it up via this reduced expression, but you get the exact same thing with t and s switched. Okay? And that's the relation that you get. This relation is actually giving two different ways of expressing HW0. One is an algebraic equation starting with s, and the other is an algebraic equation starting with t. For the two different reduced expressions. So then the question is, how do you actually compute these coefficients? How do you very quickly say what HW0 is? Okay. And I have not so much time, but the answer actually has to do with SL2 representation. And this is going to be an important point in a future lecture, I think on Thursday. So I'm not going to overstress it now because you'll see it again. But there's a very similar recurrence relation here. Okay? So I should say there's sort of one exception to this, which is that if this doesn't end in TST, if it just ends in T. So the exception to this rule is that HT times HS is just HTS. So the very first step, you just go up. You don't also split off something below. Okay? So because you can't cross off the last T, there's nothing left. You're not gonna, you don't want to get back to the identity. That's a mistake. Okay? So so we have these two rules that at the very beginning, if you right multiply by HS, you just go up. And then after that, if you right multiply by HS, you go both up and down. Okay? So there's a similar relation in SL2 representation theory. There's an irreducible VD of dimension d plus 1 of highest weight d. And there's the standard rep V, which happens to be V1. It's two-dimensional. And the rules for tensoring are that at the beginning, if you take V0 and you tensor with V1, you get V1. But after that, if D is bigger than 0, if you take this and you tensor with V, you get VD plus 1, you go up, and then you also get VD minus 1, and then you go down. This is sort of the exact same recursive formula. Okay? So this relation, writing HW0 in terms of this and that, is exactly the same rule as writing VD in the Grothendieck group as, say, some sums of tensor products. Okay, so to give the equivalent thing is the statement that V3 is equal to V cubed minus 2V in the Grothendieck group of SL2 representations. Okay, so there's 4 things here and 3 things there because there's this indexing that starts with length 0, but this starts with length 1. But once you work out the thing, these things are called Clebsch-Gordon coefficients in SL2 representation theory. So that's another way of seeing where these things come from. So this gives you a whole lot of things to play with, and there's an exercise sheet that gives you a lot more things to play with to get used to Hecke algebras. I originally thought I was giving this lecture yesterday, so you'd have 2 days to do the exercises, but yeah, you can hold on to them and take as long to do them as you want. So I think I'll stop.